Hello viewers, in today's class we are going to discuss another important problem from integral inequalities. And in this class we are going to use a very important result from definite integrals which can be used to solve or to prove this inequality, right? So here we have to show that the mod of or the absolute value of the integral 0 to 1 square root of 1 plus x square times 1 plus x raised to 4 is less than or equal to 2 times square root of 10 divided by 5, right? So we'll see a new inequality or a new result which is also known as Cauchy-Squarge inequality, which will be used to prove this integral inequality, right? So let us first see the statement of Cauchy-Squarge inequality. So Cauchy-Squarge inequality states that if we have two functions, say f of x and g of x, right, and these two functions are integrable and continuous in the interval a comma b, right? We can also write it as x greater than or equal to b and less than or equal to a and b, right? Okay. So now if fx and gx are two continuous functions and integrable functions, and if the square of this function, that is f square x and g square x, are also integrable, right? So if the square of this function and the square of this function are also integrable in the interval a comma b, then the Cauchy-Squarge inequality states that the absolute value of the integral a to b and f times g, that is here we are using the notation simply f for f of x and g for g of x, right? So the absolute value of this integral is less than or equal to the square root of the product of these two integrals, that is a to b f square dx, and then we have the integral a to b, and here we have g square dx, right? So this inequality is known as Cauchy-Squarge inequality, and this inequality plays a vital role in proving a lot of other integral inequalities. So let us first take this integral as I, which is inside the mod function symbol, right? So we can take I is equal to 0 to 1 square root of 1 plus x square, and here we have 1 plus x raised to 4, and this is dx, right? Now let us express this integral like this, that is a to b f times g dx. So for this, what we will do, see, a is 0 and b is equal to 1, right? So lower limit is 0, upper limit is 1. So we can now write this integrand as 0 to 1. Here we have square root of 1 plus x square, and then we can write it as 1 plus x raised to 4 dx, right? So now this function may be taken as the function f or f of x, right? And this function may be treated as g of x. So now we have an integral a to b f times g, that is the product of f and g. So f is square root of 1 plus x square and g is the square root of 1 plus x raised to 4. So now let us calculate this integral, right? So let us take this integral as I1. So I1 is integral a to b. Here a is 0, b is 1. So we have 0 to 1 and f square. So f square is square root of 1 plus x square whole square, and here we have dx. So this is 0 to 1, and simply we can write 1 plus x square, because the square root get cancelled with this square, and we have simply 1 plus x square dx. Right, now we have a simple integral. The integral of 1 plus x square is simply x plus x cube over 3. Limits are from 0 to 1. Now substituting the limits and taking the difference, we have 1 plus 1 cube over 3 and minus, then we'll take 0. So this is 0 plus 0, and here we have 1 plus 1 over 3, that is 3 plus 1 over 3, that is 4 over 3. Right, now let us take this integral as I2. So I2 can be written as integral a to b. A is 0, b is 1, and g square. So here gx is square root of 1 plus x raised to 4. This is square, this is dx, and now we have 0 to 1, and square root sign, it get cancelled with this square, so we have 1 plus x raised to 4 dx. So this is x. Integral of 1 plus x raised to 4 is x plus x raised to 5 over 5, and limits are from 0 to 1. Now we can substitute the limit. So we have 1 plus 1 raised to 5 over 5 minus 0 plus 0. Right, so this is 1 plus 1 over 5, that is 5 plus 1 over 5, that is 6 over 5. Right, so the value of I1 is 4 over 3 and I2 is 6 over 5. So now this Cauchy-Schwarz inequality, it assumes the form, if we take this integral a to b f g dx as I, because I is our this integral, so we have mod of I less than or equal to, we have square root of I1. Here we have I1 and then we have I2. Right, so this is square root of I1. I1 is 4 over 3, I2 is 6 over 5. Right, so now we can simplify this expression. So we have here square root of, this is 3 2s are 6, this is 2 4s are 8, 8 over square root of 8 over 5. So now mod of I is less than or equal to square root of 8 over 5. This can be written as 2 root 2. Square root of 8 is 2 times square root of 2 divided by square root of 5, and we can rationalize it. So we have here square root of 5 over square root of 5. So this is 2 times, this is 2 5s are 10. So this is square root of 10 over 5. Right, and this is our desired inequality. Right, because I is this integral, so mod of I is less than or equal to 2 times square root of 10 over 5. Right, so viewers, this is how by making use of this important inequality, which is known as Cauchy-Schwarz inequality, we can prove these kind of integral inequalities. Hello viewers, in today's class we are going to discuss another important problem from integral inequalities, and in this class we are going to discuss a very nice problem from integral inequalities, in which we have to show that the absolute value of this integral, that is 0 to pi by 2 x times the square root of cosine x, is less than or equal to the square root of pi cube over 24. So to prove this inequality, we'll make use of an important result from definite integrals, that is known as Cauchy-Schwarz inequality. Right, so let us first see the statement of Cauchy-Schwarz inequality. See, if we have say two functions f of x and g of x defined in some interval, say a comma b, right, and fx and gx are both integrable and continuous functions. right? So now if the square of this function, that is f square, and the square of this function g of x are both integrable in the same interval, that is a comma b, right? So if f square and g square are also integrable from a to b, then the Cauchy-Squarz inequality says that the absolute value of the integral from a to b f times g dx is less than or equal to the square root of the product of these two integrals, right? So the first one is from a to b, f square dx, and then we have a to b g square, and here we have dx, right? So this statement is known as Cauchy-Squarz inequality. So here we have the absolute value of the integral from a to b, and here we have the integrand as the product of f and g, right? F and g, and here less than and equal to square root of the product of these two integrals. The first one is from a to b f square dx, and then we have a to b in g square dx. So we'll apply this result to prove this integral inequality. So let us first denote this integral which is inside the mod function is by I, right? So I is 0 to pi by 2, and we have x times square root of cos x dx, right? Now see, if we compare this integral with this one, that is as a to b f times g dx. So if we compare these two integrals, we can easily see that a is 0, b is pi by 2. The lower limit is 0, the upper limit is pi by 2, and the function f may be taken as x, and the function g of x may be taken as square root of cosine x. We may also interchange the functions. Either we can take g of x or f of x as square root of cosine x. So now we can easily see that both these functions are integrable, and their squares are also integrable in the interval 0 to pi by 2. And moreover, x is positive in the interval 0 to pi by 2, and similar is the case with cosine function, because cosine function is also positive in the first quadrant, and the limits goes from 0 to pi by 2, right? So let us find out, or let us substitute these values in this integral inequality, right? So now see, we have here the mod of I, because this integral we are taking as I, which is our this integral 0 to pi by 2 x times square root of cosine x. So mod of I is less than or equal to the square root of the first integral, that is from 0 to pi by 2, and f square. So here we have f of x as x, so f square is equal to x square. So here we have x square dx, and the second integral is again from 0 to pi by 2, and we have g square. So g square is equal to the square root of cos x, and here we have square, right? So this is cos x. So here we have cos of x and dx. So now let us take this integral as I1, this integral as I2. So I1 is 0 to pi by 2 x square dx. So the integral of x square is x cube over 3, and here the limits are 0 to pi by 2. So we have 1 over 3 outside the integral, x cube 0 to pi by 2, right? So we have 1 over 3. Substituting the limits and taking the difference, we have pi cube over 8, because this is x cube, and here we have 0, so this is pi cube over 24, right? So now let us consider this integral I2. So I2 is 0 to pi by 2, and we have cosine x dx. So the the integral of cosine x is sine x, and the limits are from 0 to pi by 2. So this is sine pi by 2 minus sine of 0. Sine pi by 2 is 1, sine 0 is 0, so this is 1, right? So now taking the values of I1 and I2 in this inequality, we have mod of I is less than or equal to square root of I1. I1 is pi cube over 24, and I2 is 1, right? So mod of I can be written as less than or equal to square root of pi cube over 24, and this is our desired inequality.